Welcome to Making and Treating of Steels course. Today I am going to speak about removal of carbon content is very necessary during stainless steel production process. As we all know that in iron production process the carbon content was around 3.5 to 4.5 percentage of carbon. When it is coming to the primary steel making production process, it is brought down to less than 1 percentage of carbon. And when it is been going to the stainless steel production, primary steel making production to stainless steel production process, where you need to require, for example, arsenic stainless steels, you require around 0.1 percentage of carbon. So, and for example, the other applications, nuclear and atomic stick applications, nuclear industry, you require 0.05 for to produce the interstitial steels, which was the which find an application in automobile industry. 0.03 percentage of carbon is necessary. Such kind of stainless steels. How do you reduce? For reducing the carbon content, we use similar converter just like LD converter, which is called argon oxygen decarbonator, where argon is injected from the bottom chairs or side chairs, and from the top oxygen is perched, lanced, so that carbon level will be reduced. For other type of stainless steel, for austenitic stainless steel you require more carbon to be reduced. For those things you will be using vacuum oxygen decarbonator, where reducing pressure is applied so that you can bring down the carbon content to very low, around 0.03 percentage of carbon. And this particular process, one of the important process is called the molten metal is poured after EAF, electric arc furnace melt. That particular molten metal is poured in AOD vessel, or you call it as AOD converter, and this particular converter uses a principle of combination of oxygen and argon mixture. The argon gas is purged from the side tiers, whereas the oxygen is launched from the top. So at this particular stage, if you want to add further nickel and molybdenum, these things can also be added in AOD process. Since you are reducing the carbon content as the carbon is going down, and you can add these particular allying elements to make stainless steel. And for example, if you need very low carbon content, you choose combination of AOD and VOD. For the EAF molten metal, primary steel making unit, EAF, that particular molten metal uses this combination of the converters and produces the stainless steel. And coming to the thermodynamics part involved during the decarbonation, and as well as the chromium also, chromium which was present for the production of the stainless steel, you are added ferrochrome and high carbon content in the EAF process. That particular carbon need to be reduced, chromium level supposed to be increased in the molten metal. It should not get oxidized. Those things need to be balanced. That is, for example, in the case of both chromium and carbon oxidizes when the melting occurs. How do you understand that particular point? This particular Rayleigh diagram, as it has been shown in the bottom, this is chromium plus oxygen, chromium oxygen. This line is going up, and carbon plus oxygen line is coming down. It is intersects around 1220 degrees Celsius temperature. Since it is chromium and carbon is pure state, because of this, even at a temperature of 1220 degrees Celsius, both chromium and carbon oxidizes, so that it is beneficiation for the stainless steel production process. That is why this particular point has importance in the stainless steel production process. But normal condition, when there is chromium present and carbon is getting oxidized, chromium could be with other impurities or oxide form of chromium. It required very high temperature. It should be above 1800 degrees Celsius temperatures are required. But Ellingham diagram proves that for the stainless steel production process, this particular exact temperature is good enough, sufficient to, if you maintain in the AOD vessel and VOD vessel, carbon and chromium gets oxidizes, and you can, if you want to retain the chromium, you need to add silicon or molybdenum so that it gets retained. And as we know, the chromium oxidizes in the form of oxides Cr2O3 and Cr3O4. Carbon oxidizes to CO in the case of stainless steel production process. These lines are kept in the equation, and it also include these reactions. Chromium and carbon will also react at an equilibrium state. This is next reaction. If you apply Henry's law, since chromium and carbon is dissolved in the molten metal state, you apply the Henry's law, and it is the equilibrium constant when you rewrite for this equation. This is how it appears. Since it is a gas, you will take into in terms of partial pressure, and this, if you just rewrite or rearrange these terms, you will be getting the chromium carbon ratio, and taking all other things right side, these particular Fc and Fc are the activity coefficient or Henryan coefficients, assumption of 1 weight percentage standard state, and there was few assumption and equations given. So how do you understand the chromium and carbon ratio, how much is reduced, how do we know? So if I know its thermodynamics value such as free energy or with respect to the A plus Bt form, if I give you the equation, this kind of equation developed by Illy and Cavani, can you get it? So what is the effect of chromium? And if you want to know effect of nickel, the other equation was suggested by these people. These things, most of the numerical problems will be given, and you need to work out with the simple whatever is being asked. For example, the relation, develop a relation between the chromium and carbon. So you will be doing that particular part. So how do you proceed that particular point? So let us know in this particular point. Assume that that particular ratio R is without nickel addition, or a notation weight percentage of chromium by weight percentage of carbon, with 10% of nickel addition R dash. With respect to the temperature, if I know temperature and if I know this particular partial pressure of CO value, I can tell what is the ratio of chromium and carbon, right? These values are given in the next slide. So how do you proceed? For example, the higher the temperature, as the temperature is increasing, this particular table is explained. For example, if temperature is increasing, R and R dash, as the temperature is increasing, it is also increasing at all partial pressures, 1 atmosphere pressure, 0.25, 0.15. As partial pressure is decreasing in the row wise, temperature is increasing. This R values and R dash values without nickel addition, with 10% of nickel addition, are increasing. These problems, when you substitute these values, you can calculate from the previous slide. These things will be given in the numerical problem. This is, assume that this is also one numerical problem solution, and try to solve similar kind of problems in the numerical methods by steel making Dr. S.K. Datta textbook. Refer that particular textbook for knowing more and more problems, such kind of things. For example, at higher temperature, it suggests that higher temperature is required. You need to suppress the chromium oxidation. Chromium supposed to be retained in the molten steel, whereas carbon supposed to get oxidized. For that you need more and more temperature. This is witness. And another point is, as the partial pressure is decreasing 1, 0.25, 0.1, this particular R and R dash values, if you take any of the row at a temperature, this is also increasing. This is point about rho, and nickel is also increasing with this particular point, same point, as a PCO values, partial pressure of carbon monoxide values are decreasing, nickel is increasing, and this particular observation suggests that you need very high temperature to remove the carbon and retaining the chromium, and in addition to that, if you retain more chromium percentage for production of the martensitic stainless steel, austenitic stainless steel, you will be adding the other allying additions such as molybdenum, vanadium, so that it can retain. And if you want more and to be retained, you need to choose reducing atmosphere, reducing pressure, such as VOD vessel. This particular process takes place in the vacuum oxygen decarburizzer, so that you can achieve this particular aim. And think about this particular point, that at lower temperature chromium oxidizes first, refer the Ellingham diagram, whereas at higher temperature chromium oxidizes and suppresses the carbon oxidizes, suppress the chromium. Is it true or false? Give your opinion as a poll of vote. Thank you.